These are notes part 1 for Lagrange error bounds. It'll be the last day or lesson of new material, so kind of bittersweet. Great to be done, but sad to be done. Anyway, it's just another method for putting bounds on your error that you get when you're using a polynomial to approximate a function. And so right here, let me just kind of show you what that means. Suppose you were using a third degree polynomial to approximate a function. So suppose we did a third degree Taylor polynomial. And remember what that would be. It'd be f of c. Here, I'm going to write that a little bit better. So don't write this in your notes, just kind of watch. So if we had this third degree Taylor polynomial at some center, and it would be f of c plus f prime of c times x minus c over 1 factorial plus f double prime of c times x minus c squared over 2 factorial plus f triple of c over 3 factorial times x minus c cubed. And I didn't put plus dot 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 because this is a finite third degree polynomial that I'm using to approximate a given function. And sometimes we know what the function is, sometimes we don't. But keep in mind that this would be the third degree polynomial, but I'm going to have some error. And if I had continued this forever, what we call the rest of this stuff that I didn't include, the 4th, 5th, 6th, 99th out to infinity degree polynomial, we call that the remainder after 3 of the function. And again, the subscript is giving me the degree of the polynomial that I'm using, so keep that subscript in mind. So what I know is that my polynomial plus my remaining terms after the third degree polynomial will equal f of x. And what we're primarily concerned with is this in this section. We want to know what will that remaining chunk be, the missing piece, otherwise known as my error. Well, my error will be exactly the total value of the function minus my approximation, which makes sense. And what we're going to be doing is trying to find a bound for that error. So at least we know how close we are. So at least we know if we want to be within 1/1000th of the actual value of the function, we'll know how far out we need to go to achieve that goal. So Louis Lagrange came up with what's called the Lagrange error, sometimes called the Taylor error. And what he said is this error, which sometimes you can even call E sub n of x, is equal to the absolute value of the distance between my approximation using a Taylor polynomial of nth degree and the actual function itself. That makes sense. The total minus my approximation gives me the error. And he came up with this formula for it. What does that formula actually say? We'll get down to that in just a minute, but you'll notice that what we've got here is n plus 1 factorial, the n plus 1th derivative, and the n plus 1th degree. So very similar to our alternating series error, we go to the n plus 1th term. So we focus on the n plus 1th degree term. I kind of misspoke there when I said the n plus 1th term because sometimes the degree and the term number do not match. So it's really the n plus 1th degree term. It's really the next term. It's very similar to the alternating series test where we said in the presence of an alternator, our error is at most the absolute value of the first unused term. Well, on this one, my error is equal to the next derivative evaluated at some number, and that's what we need to talk about, over n plus 1 factorial times x minus c to the n plus first. What does that mean? It means if I was talking and using about a third degree Taylor polynomial to approximate my function f, my error or my remainder after 3 will equal the fourth derivative evaluated somewhere over 4 factorial times x minus the center to the fourth in absolute value. And sometimes you'll see both of that in absolute value. It's really not necessary, but it's good to know you're doing the absolute value of the fourth derivative evaluated at some spot. And that's what we're going to talk about next. And we're not going to let that z bother us, but let's go back up here. So this is basically what I just told you, that we have some function that is equal to a Taylor polynomial of degree n, sometimes a Maclaurin of degree n if we're centered at 0, and sometimes we just call that a polynomial of degree n. And we're going to use that to approximate the function. And there's going to be, obviously, because we go out to infinity with our Taylor polynomials, there's going to be some leftovers. That leftover is what we call the error. And again, I'm repeating this quite a bit. And what we're going to try to do is, we won't be able to get the exact error. What we're going to do is put a bound on it. So it says, when applying Taylor's formula, we would not expect to be able to find the exact value of z. And you don't need to worry about that. We are merely interested in a safe upper bound for the n plus first derivative at z. So what does that really mean? For now, it means this. Don't worry about z. Okay, I'll explain what it is, and then it'll come. You'll get it once we do a few examples. We are not going to get z exactly. We're just going to give it an upper bound, but it is merely some number in, and so we're going to have this function that's going like this, and we're going to have some center. And we're going to be evaluating at some x pretty close to the center. What z is some number in the interval from c to x, or from x to c if we went this way. Let's put a little or in there. That maximizes the n plus first derivative, but we're not going to get it exactly. We're going to put a safe upper bound for it. So let's go take a look and put this all into play. So there's several ways that College Board will assess you on the Lagrange error bound. The first one is in your face, where you don't even know what the function is, but they kind of give you all the ingredients and you just need to mix them up in a bowl. So let's take a look at what we've got here. We've got a function with 5 derivatives. That means it's continuous. I can derive it for sure 5 times on an interval from 2 to 3. It is giving me the 5th derivative's upper bound for all the x in the interval from 2 to 3. And we're going to use a 4th degree. So notice what they're doing. They're giving me a boundary for the 5th derivative. I don't even have to find it. A 4th degree Taylor polynomial for the function at c equals 2. So this is what I've got. I've got a center at 2. And an x at 3. So I'm going to be moving 1 away from the center of some function f. I'm going to use a 4th degree Taylor polynomial to approximate that. So let's just make a fakie. Boom. And here's my c. And I'm going to fit a 4th degree Taylor polynomial, and I want to know what is my boundary for my error. How confident can I be that the green curve is within a certain distance from the blue function? And here's how we start. It's at a 4th degree Taylor polynomial at 2. So we're going to create that. My polynomial at 3, x is 3, is going to be used to approximate f of 3. And so make sure you put an approximation symbol there because we're going to be approximating using a 4th degree Taylor polynomial. What does that look like? It looks like f of c, f of 2, plus f prime of c, 2, times x minus c. And that's bugging me that that's blurry, so let me fix that. F prime of 2 times x minus 2 over 1 factorial plus f second derivative evaluated at 2, x minus 2 squared over 3 factorial plus f triple prime at 2 at x minus 2 cubed over 3 factorial. I am just writing out Taylor's formula out to the 4th degree. And because I am using this to evaluate it at 1, I know that furthermore, this is f of 2 plus f prime of 2 times 1, right? Because I'm going to be doing x is a 3 in this case, plus f triple prime at 2 times 1 squared over, 2 factorial, plus f triple prime at 2 times 1 cubed over 3 factorial, plus f 4th derivative, 4 factorial, times 1, man, I'm making a lot of little mistakes here. Anyway, that is what I call a 4th degree Taylor polynomial. I am looking for how accurate that is. Remember when I drew that green curve, how close is it to the actual function f of x? And we don't know what f of x is, but the Lagrange error model says that the remainder after the 4th degree term at x, and we'll replace that right now, for us, it's going to be at 3, is equal to the absolute value of, and I go to the next term, the 5th degree evaluated at some unknown number over 5 factorial times x minus 2 to the 5th. But my x is a 3. So really what I need to do is figure out what is the 5th derivative at z. And remember I said I don't really care what z is. I'm going to overshoot it. And so z is some number in the interval from 2 to 3 where the 5th derivative gets maximized. But they told me right here that I am for sure confident that that 5th derivative is less than 0.2. So I do 0.2 over 5 factorial times 1 to the 5th. And it said to go to 3 decimal places. So if you go do that on your calculator, you'll get 0.002. That's how close my approximation using the 4th degree Taylor polynomial is to the actual function. Now it says, suppose that what you got when you plug, again, we don't know what f is. So I am kind of stuck up here because I don't know how to evaluate these. They didn't give me an explicit function for f, but they are telling me what that approximation is. They're saying that's approximately 1.763. Well, and I know I'm within 0.002 of that. So for me to find an interval where the actual function value at 3 must reside, I know that it's got to be an element of the interval where I take my approximation minus 0.002 and my approximation plus 0.002 because that is my maximum amount of error. So if I go down that and up that, I will have a safe interval for f. And if you do that on your calculator or in your brain, you will get this. And I'm going to define this function or this interval as capital I, which is legal as long as you define it. And then it says, well, could f equal 1.778? Is that what it could be? Well, No, because I'm not in my confidence interval. That's what they call it in statistics, is a confidence interval. So I'm going to say no. 1.778, and when it says why or why not, this is all you need to do, is not an element of my confidence interval. Could f of 3 equal 1.764? Well, yes. Why or why not? Because 1.764 is an element of my confidence interval. So notice on that one, I was given a function that wasn't explicitly defined. It was just some arbitrary function f. But I just used my model, and I said, don't concern yourself with z most of the time. They are telling you a bound for the fifth derivative. All right, now let's move along to the next one. I'm going to do 2 here, and then I'll make another video for the other 2. So now I'm given an actual function. My function is sine x. This is a kind of where we have to appreciate the historical value of what's going on here while still knowing that modern technology has replaced the need to do this. But we're going to do it how they would have done it historically, but kind of no, I no longer need to approximate sine of 1. I have a graphing calculator that would do that. And actually, I don't have a graphing calculator on me right now, but go to your calculator, make sure you're in rad mode, and do sine 1 and put it in a little box right there. There's no need for us to do these approximations for sine. Now, this process is used in some higher levels of science and stuff when they do have some function that they can't wrap their brain around, and they try to find a polynomial that mimics it with a certain amount of accuracy. So it says 5th degree, Maclaurin, so my center is at 0. Polynomial for sine of x. Let's go do that right now. We should have that memorized. So my Taylor polynomial of 5th degree, which sometimes we can call P sub x, or even because this is Maclaurin, you could even call it big M sub x. We're going to use that to approximate f, and f is sine. So actually, let me write this a little better. So we are going to take sine x and approximate it using a 5th degree Taylor polynomial. And we know that the 5th degree Taylor polynomial for sine x, my smartboard's kind of locked up here. Shoot, it's not writing. I'm going to give it a minute to settle in. So I'm going to write our memorized 5th degree Taylor polynomial for the sine of x. Sine is an odd function, so I need to start and use my odd degrees. Remember, it goes x minus x cubed over 3 factorial. I'm sorry. I'm waiting for my smartboard to kick in here. I'm not sure what the issue is. I think it's totally died. That might be as far as I can get in this video, and I will have to pick it up from there. I'll make a separate video. My smartboard is just locked up on me, so log in and there'll be another video later.